So we'll give it another 30 seconds. Okay, we'll go ahead and get started. Let me just admit these people. Okay, well, I appreciate all types of music. Can we mute your mic if you're not speaking? Thanks. Okay, so again, we're going to start with a QR code for the molecule of the lecture. Then we'll have, it looks like, 6 or 7 questions on that. We'll do some of the think, pair, share activities, and then we'll get back to the workbook. So as I mentioned in a couple of the announcements, please make sure that you are keeping up with doing some homework problems each day from the homework sets and the Orion sets. Then you're going to have your first exam coming up this August 31st, Monday. So here's our molecule of the lecture QR code called Tamiflu. So if you want to get your phone out, scan that, bring up the qrchem.net. And again, if you're new to joining these chat sessions, the purpose of this activity is to show you that even though we're drawing stuff on slides and your handwriting stuff is flat, these molecules exist in 3D. They have a 3-dimensional shape. The shape arises from the hybridization of each particular atom. So if we're thinking big picture, carbon, nitrogen, oxygen, halogens, they all have different bonding patterns. When they bond together, they're hybridized in a certain way. The hybridization leads to bond angles, and that gives rise to the shape of the molecule. So our molecule of the lecture is known as Tamiflu. So it's a neuraminidase inhibitor. And basically what that is, if you look at this word here, neuraminidase, the ASE is indicative of an enzyme. An enzyme is a large molecule in your body that performs a chemical reaction, a specific chemical reaction. This particular enzyme cleaves glycosidic linkages. And so while we're not going to specifically go into a lot of mechanism of action of these small molecules, if you take biochemistry, you will. A glycoside is basically a sugar or a carbohydrate. We get energy from carbohydrates, and that enzyme basically cleaves them. So the structure is shown here, and you also have it on your phone so you can spin it around. And I encourage you strongly to really take note of, these hybridizations. Like when you look at this part of the molecule, you can see that that part of the molecule is relatively flat. Then when you get into these sp3 hybridized carbons, you can see now that that part of the molecule has more shape. It's out of the plane. And if you align the structure on your phone, similar to how it's presented on the screen here. So I'm just rotating around here on my phone. So I've rotated my structure around. So how it looks like how it's drawn on the screen. Just as a refresher, these lines that are sort of just solid lines, those are basically, we can say, like in the plane. These dashed ones indicate that that bond is going back. So as you look, this bond where my mouse is, you can see the oxygen atom here. There's a hydrogen pointing up. So again, it's implicit that there's a hydrogen here because this bond is going back, the hydrogen's pointing up. And we see that on the phone, the molecule on the phone. So this carbon-nitrogen bond is up. The hydrogen there that is there is down. Now we have another hydrogen that's up. So as you spin your molecule, you'll see that this hydrogen here and that hydrogen there are both up. And so you can see that on the molecule as well. So the bold line means it's coming towards you. The dashed line means it's going away from you. This dot right here, this means that this molecule is formulated as a salt of phosphoric acid. We have a basic nitrogen that is forming an acid-base reaction with phosphoric acid. And the reason that things are formulated like that in these pills is it gives it better oral availability. So what does that mean? You take a pill, you swallow some water, it goes into your gut. This helps your stomach basically digest the molecule when it's in this form. So the molecule is made by Roche. Roche is a large pharmaceutical company. Genentech is a subsidiary of Roche. I have these two other pictures here. Shikimic acid. Shikimic acid is isolated from the Chinese star anise. So this is a natural product, as we say. It's a plant that contains this. This plant produces this chemical. That's a natural product. The chemists at Roche and Genentech have taken this material and transformed it into Tamiflu. Tamiflu is a synthetic substance. It doesn't grow anywhere on Earth in any form or fashion. It's synthesized in a lab from shikimic acid. What I hope you can do at this point is appreciate that this ring here is this ring. You have a pi bond, then this functional group. This functional group has been transformed into a different one, right? Now this oxygen, CO, has been transformed into CN. And notice the bond has been inverted, right? So we call that stereochemistry. The stereochemistry of this bond has been inverted. This one has been inverted as well to that one. So we're sort of mapping one structure onto another. So what is the big picture of this class in general? Is you're going to learn reactions of how all these things are transformed into these functional groups. And then, as we said, this molecule is an antiviral. Basically, about in 2005 to 2007, the avian bird flu was proposed, or was, I guess, going to become a global pandemic. It didn't quite pan out that way, but this molecule was shown to treat the avian bird flu. So let's go ahead and ask some questions about it. So here's Tamiflu. Again, this part of the molecule is not going to come into play for these questions. It's just there to show you that the molecule is formulated as a salt. So how many sp2 hybridized carbons are present in Tamiflu? So in the chat, go ahead and throw in a letter or a number. So if we remember that an sp2 hybridized carbon, visually, what are you looking for? You're looking for 3 sigma bonds and 1 pi bond. That combination of bonds gets you your 4 bonds to carbon. So if we identify them, there's 1, 2, 3, 4. So of the sp2 hybridized carbons, how many of those 4 have hydrogen atoms bonded to them? So the majority of responses are zeroing in here on answer B, which is 1. Only this sp2 hybridized carbon has a hydrogen. This, and this one do not have hydrogens. So how do we know that? When I'm looking at this carbon, I see 1, 2, 3 sigma bonds. The 4th bond is the double bond or pi bond. None of those atoms are hydrogen. Here, we're not showing a bond. Again, so that's implicitly bonded to hydrogen. We have 1, 2, 3 sigma bonds. There's the pi bond. This one, we're explicitly showing all the bonds. 1, 2, 3, and then the pi bond. And the same for this. 1, 2, 3 sigma bonds. The 4th is the pi bond. Okay, so new question, how many sp3 hybridized carbons are present in Tamiflu? So in the response, I see Garima is hedging her bets with a question mark after her response. I appreciate that. The answer is D, as in dog. It is 12. So again, what is an sp3 hybridized carbon? It's a carbon that has four sigma bonds. So let's track them or map them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what's our next question here? So of all 12 sp3 hybridized carbons, how many are classified as methyl groups? Garima has confidently put down 4. 4 is the correct response. Let's map them out. So 1, 2, 3, 4. Let's move on to the next question. again, of the sp3 hybridized carbons, how many are classified as methylene? So again, this is we're gaining resolution amongst the different types of carbon in this molecule. So how many of the sp3 hybridized carbons are methylene groups? So the consensus in the chat is 4. That's correct. So let's map those out. 1, 2, 3, 4. So a methylene group is a CH2 group. So again, 1, 2, 3, 4. Let's go on to the next one, which I believe are of the sp3 hybridized carbons, how many are methine groups? So again, we're considering sp3 hybridized carbon only. We have a smattering of answers here. What do we mean by methine? How do we classify methine? So it's CH. So again, we're only considering sp3 hybridized carbon. So by my count, the correct answer should be 4. So 1, 2, 3, 4. So what is the big picture of me asking you these questions? So again, on the Bloom's taxonomy, these would sort of be on the lower foundational levels of Bloom's taxonomy, sort of like understanding, remembering. How are we going to use those type of questions as we advance through organic chemistry this semester? We're going to learn chemical reactions that can take place in different parts of the molecule. And you look at that and you say, that is a very complex molecule. How do I know whether it's going to happen on this carbon or this carbon? Well, first you need to classify all the carbons like we just did in those questions. And then, so we've sort of resolved them, right? We've taken all the sp3, we've resolved them between methyl, methylene, and methine. So as we learn chemical reactions, we can say, okay, this reaction only acts upon methyl groups. And so we've eliminated the methylene and methine. So we know, okay, the reaction can only take place here, 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 or here. So when we look at something that may seem complex, we can use rational thought to really pinpoint where the reaction can take place. So that's what we're doing in this first module here. If you're a Pink Floyd fan, we are learning to fly. It's a great song, you should listen to it. So our next question here Here's Tamiflu, and again, we're ignoring the phosphoric acid salt. Visually inspecting this molecule, what is the sum of the pi bonds and the rings? So the consensus is 4. Of those 4, how many are pi bonds? There's 3, right? How many different types of pi bonds do you see? So yeah, there's 2. We have a carbon-carbon pi bond. We have a carbon-carbon pi bond. Then we have carbon-oxygen pi bond. So of the 2 types of carbon-oxygen pi bonds, are those the same type of of carbon-oxygen double bonds? So is this double bond the same as this double bond? What do you think? Just type yes or no into the chat box. What am I asking you? Look at the environment of that CO pi bond. Does it have the same bonding environment? Bria has an emphatic no. She used all caps. So they are not the same. So even though we're looking right here, that's a CO pi bond, CO pi bond. They're not the same because look at this bond here. This is to oxygen, that's to nitrogen. So we've effectively taken those 3 pi bonds. One of them was carbon-carbon, 2 of them were carbon-oxygen. And we've now made a distinction between the CO double bonds because they're in different bonding environments. So what does that mean? That means that this collection of atoms here is a unique functional group. This collection of atoms is a unique functional group. So as you go through chapter 2 reading, you're going to hit sections about carbon or polar organic functional groups. So as we put heteroatoms into molecules, again, a heteroatom is something like oxygen or nitrogen. As we form these different bonding arrangements, those are called functional groups. They have specific names. So on Friday's chat, we'll do more exercises related to that activity. But for now, we're going to transition into another exercise, thinking about what you just did in a different way. So you visually inspected the molecule. You counted there was 1 ring, 3 pi bonds for 4 total, right? So those are called the degrees of unsaturation. So Columbia is asking, does it have to do with the fact that oxygen is more electronegative than carbon? That would deal primarily if we were assigning a dipole moment to things. So what I want to do now is I think we're all comfortable with what this question's asking. But what if I flipped it around and asked you that question in a different way? So we're going to do it sort of with the structure on the page here. And then we're going to do the same exercise, but using sort of a very simple algorithm. Recall that the general formula for an alkane. An alkane is fully saturated. Every carbon is either bonded to a carbon or a hydrogen. The molecular formula is CnH2n plus 2. Whatever N you put here, you then put there, and that tells you you have an alkane. So we need to use that to figure out, for any other molecular formula, the number of pi bonds in rings that are embedded in a given molecular formula. So let's go through this. Given a structure, determine the molecular formula. So ignoring this, H3PO4, ignoring that, what is the molecular formula for Tamiflu? So take some time to do that. Throw your answer in the chat. So how many carbons do you count? So we have C16. Can everyone see the document cam? There's 16 carbons. Aiden's thrown his response in the chat. It's very blurry. Does that help? So hydrogens, we have, Aiden says 28. Does everyone count 28 hydrogens? The nitrogens are pretty obvious. There's 2. Oxygens, there's 4. So what are we trying to do? If we're given this molecular formula, say you didn't even know what that structure was. If you were given this, how do you then determine that? So let's follow this algorithm on the slide deck. We're on step 2 now. All heteroatoms must be counted as hydrogens according to the following rules. Oxygen we ignore. So this is C16H28N2. We're getting rid of the oxygen. The oxygen does not affect the hydrogen count. Nitrogen atoms subtract 1 hydrogen each. We have 2 nitrogens. So now we have C16H. These 2 are going to subtract off from 28, so we get H26. Halogens such as fluorine, chlorine, bromine, or iodine add 1. There are none of those. So this is what we are given here. We went through our algorithm. This is what we are going to use to compare to the saturated alkane. We have N equals 16. So if we're using CnH2n plus 2, for 16 carbons, we want to determine how many hydrogens there should be. So how many should I write here? So give it another couple seconds for people to plug in some responses to make sure we're coming to a consensus. So we've pretty much zeroed in on 34. So this is our revised molecular formula here, C16H26. We just determined what the molecular formula should be based on 16 carbons. So this is the number of hydrogens 16 carbons should have. So what we're going to do is take C16H26 that we determined right here and sort of just subtract them. Those cancel out. We're left with H8. A degree of unsaturation is defined as 1 molecule of H2. So I'm going to take H8, divide that by H2. 8 divided by 2 equals 4. So remember what you did by visually looking at the molecule. You counted 3 pi bonds plus 1 ring. So that gets you 4, right? So notice that's what we just calculated. So again, 2 times 16 plus 2, that gets us our 34. So you can visually look at the molecule, count the pi bonds or the rings, or if you are given a molecular formula, you can do the same thing using this algorithm. And why are we learning this? The substance that you see on the screen, Tamiflu, as I mentioned, those different functional groups. How do we as humans know those functional groups are there? This thought exercise we're doing helps us to differentiate or determine that. And it's all related to what we do in Module 2 when we start learning about spectroscopy, which will really tell us how these atoms are connected to one another. So if you didn't know the structure, but you were given this molecular formula, and you found that there were 4 degrees of unsaturation, you can then start thinking, hey, I know that a degree of unsaturation is a ring, can be a pi bond. I know what type of pi bonds can exist. I can have CC pi bonds. I can have CO pi bonds. I can have different size rings. So it's really meant to get you thinking about how to connect atoms together to make functional groups that will fit that molecular formula. So I've been getting a couple questions through Canvas and email about constitutional isomers. So we left off the last chat with this think, pair, share about C4H8. And this is related to constitutional isomers. Notice on this slide deck, there is not a structure shown. So if you're given a molecular formula, C4H8, run through the calculation we just did. So given C4H8, how many degrees of unsaturation are present in that molecule? If we use CnH2n plus 2, n is equal to 4, C4H2 times 4 plus 2, that's C4H2 times 4 is 8 plus 2, that's 10. For 4 carbons, for a fully saturated molecule, there should be 10 hydrogens. But we are given this that only has 8. So we subtract C4H8, we get H2. A degree of unsaturation is 1 molecule of H2. That equals 1 degree of unsaturation. A degree of unsaturation can be a pi bond. It can be a ring. Now what you need to do with this information, propose constitutional isomers that have 1 degree of unsaturation, either showing a pi bond or a ring, and have this molecular formula. So let's take a couple minutes. You can start drawing things out, show them up to the camera. As people propose them, I'll redraw them here so that you can see them on the document cam. Okay, so I'm going to start a category here. I'm going to call these rings. I'm going to call these pi bonds. Aiden has put up the following in his. So Hannah has the following. Need to scooch the camera a bit so you can see that. Hannah has another one. So I put those down. I put the pi bond under pi, the rings under the rings. Whoops, this is a mark. Don't pay attention to that. So I apologize for the document camera. Hopefully it's auto-focusing now. Is it focused enough that you can see what's happening? So we have again the molecular formula C4H8. We've proposed 1, 2, 3 constitutional isomers. Maybe Aiden scooch over a little bit. Okay, there we go. So Aiden proposed this one now. I think we have 2 more we can propose. So why do I like this exercise? I really like this because I think it's a puzzle problem. I like these a lot because you're given something as simple as this molecular formula, and you can let your mind run wild proposing these different structures. So Taka has proposed the following for the pi bond. I think there's one more. Aiden, if you could move over a smidge. Okay, Aiden has another one. And that should be it. I don't think there's any other possible combinations that you can put down that would not violate Lewis dot rules. So let me show you sort of why I wrote them this way. There's the molecular formula. I'm going to draw a line here. On this side are the ones with pi bonds. This side are the one with rings. And I want to draw a line here. In here, I want to put the number 4. In here, I'm going to put the number 3. So a logical way of approaching this is the number 4. These are all basically linear molecules that keep track of 4 carbons with the pi bond. So here the pi bond starts at position 1. For the next one, it moves over position 2. Now for the ring, it doesn't matter where you start really, but that ring has 4 carbons in it. Down here at the 3, I'm going to start here and say 1, 2, 3. That's a 3 carbon chain. Now we have a 3 carbon ring. So this is just a way to organize things so that you're not proposing the same structure more than once. So Columbia is asking, what is the difference between the second and third isomers using pi bonds? They both have a pi bond between the same carbon atoms. And yes, that is 100% correct, but there is a difference. Notice in these pi bond, all of these are constitutional isomers. The pi bond here starts at 1, it ends at 2. Here it starts at 2, it ends at 3. Here it starts at 2, ends at 3. The difference is, look at this methyl group at 1 and 4, and then here 1 and 4. So they are on opposite sides of that pi bond, right? So these are same. These are now different. So one thing that we're going to learn over the course of this semester is that ties into this. Yes, they're all constitutional isomers. They have that molecular formula. How do you and I communicate that I'm talking about this one and not that one? And so the way we do that is through nomenclature. So let me give you a brief preview of that. These are the C4 constitutional isomers. The parent carbon for C4 is called butane. Butane. But because we have a pi bond, this is an alkene, so it's butene. B-U-T-E-N-E. The butene tells you there's a pi bond. So this molecule, we can say 1 butene. The 1 tells you where the start of the pi bond is. So this molecule is obviously different because the pi bond starts at position 2. So it's 2-butene. But this molecule here is also 2-butene. So how do we differentiate these? Well, the fact that the 1 and the 4 groups are on the same face, they're the same. The word we use for that is cis. Cis means same, cis-2-butene. Here, the 1 and the 4 methyl groups are on opposite faces. The word we use for that is trans. I can't fit it right there, so I'm going to say trans. So trans-2-butene. Now, because this is a ring, we call this cyclobutane. Notice that it has an ANE ending. The cyclo tells you it's a ring, cyclobutane. So that was the 4 carbon in terms of, say linear and ring. But what if the longest chain is not 4 carbons long? It's 3 carbons now. A 3 carbon chain is propane, but since we have a pi bond, we are now using propene. The A has changed to E. The double bond starts at 1 propene, but we have to account for this group right here. That group is a CH3 group. We call CH3 groups methyl. Remember we did that exercise, methyl CH3. And it's at the 2 position. So it's 2-methyl. Now we can put all that together and call that, I don't think you can see what I'm doing. Sorry about that. So now we can put that all together and call that 2-methyl-1-propene. So now of the 1, 2, 3, 4, 5 constitutional isomers we've determined, we can now refer to them as their names. So if I don't give you any of these structures and I say, given this name 2-methyl-1-propene, you should be able to draw that structure. That's a skill that you want to be able to develop over the course of this semester. And then finally, the last one, this is a 3-membered ring, so it's cyclopropane. Cyclopropane. We have this group hanging out, which again is CH3, that's methyl. It's at the 1 position. So we would call that 1-methyl cyclopropane, all one word. So the question from Hannah, why do you start at the top for here? Why did I start numbering there 1, 2, 3 instead of 1, 2, 3? If I did it the other way, so again, this one is correct. If I did it the other way, it would be 2-methyl-2-propene. And as Aiden pointed out, the alkene takes precedence, so it should have the lower number. Again, I don't expect you to know this for exam 1. I'm giving you a preview of everything you're going to learn over the course of this semester. So, trying to adjust this here. If you look at these numbers here, 2 and 1, if you add that, it gets 3. If you look at these numbers, 2 and 2, that gets you 4. one of the nomenclature rules, when you name something, the sum of those locant numbers should always be the lowest possible sum it can be. So Tenley is asking a question. I don't like the word opposite. I want to use the word bonded. The methyl group at position 2, it's bonded to carbon number 2. So I'm going to swap out your word opposite and just replace it with the word bonded. So in this problem, we looked at a molecular formula. We determined there was 1 degree of unsaturation. We proposed all the pi bonds, all the rings you could have. We learned a little about nomenclature as well so that we can communicate those structures to each other. So I have another one of these before we move on, because there were some questions about it through email. This one is right from your book. So we're back to the slide deck here. If you're given a molecular formula, C2H4Cl2, how many constitutional isomers can you propose? So we want to determine from this given what is the fully saturated alkane for C2? So we're given N equals 2. So if the molecule were fully saturated, it should be that. And we said that halogens will add to the hydrogen count, right? We have 2 chlorines. This will actually become C2H6. So when we go through this, we actually get H0. So what this is doing is telling you that in this molecule, there are no degrees of unsaturation. So no, whatever you propose, there's no pi bonds, there's no rings. So what's a way of starting with this? You have 2 carbons. Just there's 2, right? It's hard to see a little bit. There's 2 carbons. Now we need to put in 2 chlorines. I would say just initially stick them on both on carbon 1. What's the other possibility? Put one on carbon 1, the second one on carbon 2. So Hannah's asking about the rules. The halogens will add to your carbon count. We have 2 halogens. That's why I added 2 to this to get this right here. Nitrogens actually subtract, so you would subtract them out. There's no other constitutional isomers you can draw for this. Let me show you something, because I think this may have confused people. I just redrew this molecule this way. This and this are the exact same thing. They are not constitutional isomers. This and this are the same thing. Those also are not constitutional isomers. They are equal to one another. And to understand the reason why they are the same, these molecules, this carbon-chlorine bond, the only difference between them is I did a rotation. These molecules are not stagnant. Keep in mind that a bond has energy. Bonds are always moving. They're rotating. So to get from between these two things, I've done a rotation about carbon 1, 2. So I'm going to just draw that like that. You can rotate these bonds. Those are the same thing. That's the same thing. All I've done is a rotation in the page. These are all the same. So Taka is asking about if there was a double bond. Yes, this is a different, now this is a different scenario, keep in mind. You cannot rotate between these two. So those are different compounds. They are not the same because of this pi bond. The reason you can do it up here is because these are all sigma bonds. So how would just so we can be complete, how would we name these? It's an ethane derivative, right? Ethane. There's ethane. At the 1 position, there are both chlorines. So we would call this 1,1-dichloroethane. This one, there's ethane. Now they're different. 1,2-dichloroethane. So we're able to communicate those different isomers to one another. So we didn't actually get time to go to the workbook so much, but I do have one more question I'd like to ask you that's shown about constitutional isomers. The following 4 molecules have the molecular formula C4H6O. Of the 4 isomers, which one has 4 unique carbons and 3 unique sets of hydrogens? So again, we're looking for 4 here and 3 here. So this would be a typical, I apologize, I can't get this. I'll try to get all this all. Hopefully you can all see that. Is it focused? So if this were an exam question, this is how I would sort of set it up if I were solving it. You're looking for 4 unique carbons, 3 unique hydrogens. The correct answer is D. but let's run through this in our last minutes here. For this, for choice A, how many unique carbons are there? What number should I put here? Max says 3. How many hydrogen sets? Christina says 2. 3 and 2 does not match what we're looking for, so that's not the correct answer. What about B? How many unique carbons do you see? Aiden says 4. 1, 2, 3, 4. How many unique sets of hydrogens? It's also 4. 1, 2, 3, 4. 4, 4 does not match 4, 3, so that's not the correct answer. What about for choice C? How many carbons do you see? This one is 3. So those are the same. This one is different. And then that one is different. How many unique H's do you see? There's 2. You have a methylene and a methylene. Those are the same. And then you have this CH2 here. And again, we got that from symmetry. There's a mirror plane bisecting that molecule. And then obviously D was the correct answer. So what I'm going to do is just sort of number these carbons. We have 1, 2, 3, then 4. Those are all unique carbons. They're all different. How many unique sets of hydrogen do we have? We have a methine, we have a methyl, and we have a methylene. So that's 3. So that matches what the prompt was asking for, 4 and 3. So D is the correct answer. So I'm sorry we went a little bit over time, but Friday we'll get into polar organic functional groups. So we'll start learning the names of those different collections of atoms. I'm going to post this chat in Canvas after the video renders. And please, if you haven't done so, start doing your Wiley Plus assignments so that you're all caught up. But otherwise, I'm going to go ahead and sign off, and we'll see you Friday.